Hi, my name is Dan. I'm coming from the University of Washington Bespoke Silicon Group, and today I'm going to talk about BSG Tag, which is a minimal open source ASIC configuration system. So, what is BSG Tag? It's a silicon-proven, minimal, fast, and flexible bus for chip configuration. And it's a powerful abstraction for reaching into your chip and setting registers while the chip is running, no matter what the clock domain is of the receiver. And it's a reliable methodology for stack configuration, reset sequences, and dynamic mode switching. So if you were here in 2019, you saw me present on BaseJump STL. BSG Tag is a part of BaseJump STL. BaseJump STL is a standard template library for Verilog, which provides all sorts of components for everything you need to tape out a chip. We have everything from networks on chips to individual flops and a portability layer that lets you go between different ASIC implementations, different process nodes, different FPGA implementations, and it grows every time we tape out a chip. A little bit more about BaseJump. It actually provides everything from your RTL design that you actually want to do as a value add for a researcher or a company, and then goes all the way to your prototype or your bring-up board after you've taped out the chip. So we have open source sockets, open source PCBs, open source patterns, and every time we tape out a chip, we update those repos. So switching back to BSG Tag, configuration registers are pervasive in these kinds of designs. You have IP blocks that require system configuration. These are sometimes hardened blocks that you don't have access to, so they don't parameterize. These are sometimes blocks that require mode switching or power management, clock management that's too complex to just handle in normal register buses. You have replicated hierarchical blocks that require configuration at runtime. So this is something like a multiply instantiated core in a many core. You might have different coordinates, you might have different modes in a heterogeneous system. And then you have, when you're making prototype chips, you often have these things called chicken bits, which are features that you think you want to use or you want to prototype out, but you don't want to cripple your system if they don't work. So you have runtime, after you tape out the chip, being able to isolate bugs to those areas. And then ASIC bringup also has unique challenges compared to like an FPGA design. You have unknowns between the board and the ASIC integration. They're normally developed at the same time. So you have different unknowns between different suppliers that you get, how the board's actually manufactured, the tolerances. And when you have an n=1 ASIC, you don't know exactly how the manufacturing process is going to come out. You can have your skew and tolerances spec'd out, but it never actually ends up being exactly what you want. You also have a bootstrapping problem that doesn't normally exist on, say, an FPGA, where you need a reliable method of sequencing your power and reset and clocks so that the chip comes up in the correct way. And notably different than FPGA is you can't rely on any power-up state. You can have power on, there's no reset I or initials that just happens when you turn on the chip. You need to have that explicitly in the sequencing. You could get lucky and all your clocks for all your designs could come up at full speed, which is great for benchmarking, but it might turn chip to glass. So, why not just have a naive configuration bus? I'll talk a little bit about, some of the challenges that come up with that. So this is an example that you might have. You might have a small, say, APB bus with, say, 2 modules here and then a clock generator. So one problem is the bootstrapping problem we mentioned. You can't configure the clock generator using the bus because the clock generator is not brought up yet. You have a skew problem, which is that it's very hard to share clock domains between a bring-up board and an ASIC because you have this undetermined skew that we talked about a little bit earlier. You have a pin count problem, which is that pins are extremely expensive on ASICs, especially when you're taping out, say, an MPW run with limited silicon area. You have a multi-clock problem, which is that your clocks might be different between your different components, but you want to use the same configuration bus. And you have a multi-protocol problem, which is that different components might speak different languages, so your APB bus might not map directly to those components. So for a minimal configuration system, these are the relative priorities that we want. We want to use the very fewest pins possible because, as we said, they're expensive. You need a much bigger chip to get much more pins. You need high convenience and robustness. If you want one thing to work on your chip, it's this, because everything else tends to depend on it. And you want high bandwidth per pin. This is the lowest priority, but it does help a lot for things like gate-level simulations, which take an inordinate amount of time. So having an ability to speed up your simulation or speed up your configuration will actually result in faster simulations. So this is BSG tag as our solution to these problems. It's a 2 to 3 wire interface with a clock data optional enable, fully source synchronous, and it has a standard protocol layer which allows you to have this high level of abstraction that's missing in other protocols. Highly scalable distributed master client architecture, and it handles both static and synchronous configuration across all clock domains in your system. We've taped out with BSG tag running up to 400 megahertz, which is about when you run into LV-CMOS problems. If you have a higher performance I/O, there's no practical limit to how fast it could be. So now we'll talk a little bit about a system that uses BSG tag. What does that look like? Just a quick aside, some terminology. There's system-synchronous for source-synchronous systems. System-synchronous is what most people think about when you have a digital system. You have a single clock which goes to multiple flops. And there's some timing requirement that the skew between those two, or the delay between those two flops is less than 1 clock cycle, so that when the clock hits, everything is synchronized. Source-synchronous systems send the clock along with the data. And this allows you to have the send and receive delay be effectively arbitrary, because the clock will be received at the same time, or the data will be received at the same time that the clock arrives. The benefits here are that it's much easier to synchronize, and you are resistant to local PVT variations, because if you affect your data in some way with large skew, you'll also affect your clock in the same way. So the basic BSG tag architecture here is a master client architecture where you have a sender chip sending a center-aligned source-synchronous clock and data to a tag master, which lives on the ASIC. The tag master then distributes those signals to the tag clients that actually configure it within the logic blocks. The BSG tag master is generating the individual tag lines, but the BSG tag client is interpreting them and generating the data locally. So that's an example with one tag master, but in order to scale, you need multiple tag masters. For a large ASIC, you might have a dozen per IP blocks. And we use something called a decentralized tag master, which basically filters these client requests to a local set of clients that can be configured per IP block. And then you can scale up from there. The BSG tag enable line could then be used to filter between multiple individual chiplets. And then within that, the tag master decentralized can filter down to a number of clients. So we'll take a little bit deeper dive into what those components look like and how you build this system. And again, all this code is released on BaseJump, so you can take a look. The actual components are fairly simple. The key is that they've been rigorously validated so that you can just kind of pop in and reuse them. So the tag master essentially has a reset by just sending a stream of zeros, and then as it receives a command from the tag in a serial manner, it fans out these signals to the clients into a four signal bus. And this is a very simple format. You can just basically have node ID, which is the client ID, data or reset bit, length, and then the data, which is a variable length. And this allows you to scale the tag clients to be any number of payload bits and not necessarily the same number of payload bits, which avoids like a fan out issue. Let's skip over that. The basic BSG tag client looks like this. You have the opcode and the parameter that gets set, and then a serial in, parallel out register that provides the data coming out. Now, BSG tag client unsync is the minimal BSG tag client. It has no concept of a local address, and it shifts the data in asynchronously. And this can have a problem if you're using it for a multi-bit bus, because as you can see in the top right, the data will be shifted in, and you'll see intermediate values that are not the value that you're transmitting. Sometimes this is fine if you're doing this like before reset, or you're doing this before your clock configuration. But sometimes this will actually cause glitches at runtime, because you'll have resets that will toggle intermittently, or coordinates that don't exist coming on your bus. So in order to solve that problem, we also have the basic BSG tag client. And this provides an additional synchronizer to receive to your local clock domain. So the BSG tag client will receive the tag clock and tag op, and then synchronize to the received clock of the receiver, which will only see the atomically changing values as you provide a new configuration. So now we'll talk a little bit about building stuff with BSG tag. So BSG tag is a fairly small set of components, but the key is that it allows you to build complex systems out of these basic primitives. You can construct fine-grained sequences of operations automatically so that you don't have to rely on sequencing manually during the bring-up process. And kind of the bottom line is with just a few pins, you can reach inside the chip and you can set any register while it's running, no matter what the receiving clock domain is, no matter if your chip is functional. We've had chips that are hopelessly broken that BSG tag always works. So when you're building with BSG tag, we collect these data points in a Verilog package. So this will have a BSG tag per configuration register. And then you can aggregate these into collections of BSG tags. And then you can aggregate those into collections of structures. So you have this recursive hierarchical view of your chip from the configuration register point. But the key is that because we distribute the tag masters, you're only paying the overheads for the local tag clients. You don't have an address that's the size of the entire system. You only have your local size. So this is what a very simple implementation of the BSG tag system would be. You have your tag master, a tag client unsync, a tag client, and it's synchronized to a local core clock. So just a few lines of code, and this brings you in the entire BSG tag infrastructure. In order to generate those initial tag signals that come from your sender chip, we recently started using a Verilog module itself to basically Bitbang the tag interface. So the interface for this module is you basically send a 1 or a 0 bit, and then the tag will reflect that in a source-synchronous, center-aligned manner. And by doing this, you can have programs on your sender chip dynamically configure your tags. So during bring up for a chip, you might be able to configure your tag clocks from a command line. You might be able to build this into your PCB board for just pre-programmed sequences. It gives you a lot of flexibility. And then on top of that, there's a Python layer that we usually use, which allows you to, as we said, recurse into the system and look at the different configuration registers in a hierarchical manner. So this is an example of how you would use a BSG tag script to do something fairly complex like reset a clock generator. You have the basic primitives, which are sending a single value to a single tag client, and then you can use that to assemble complex processes. And then you can use those to assemble complex bring-up procedures for things like automated testing, automated bring-up, and automated checkpoints for your designs. So we use BSG tag on all of our chips. I've lost track how many we have, probably a dozen. But BSG tag's also been used by commercial chip tapeouts, been used by academic chip tapeouts, been used on FPGA. And the key is that by using it, we're able to not consider all of this complications for every chip. Alternatives that people use are SPI, I2C, things like this, sometimes JTAG, depending on what you want to do. But the real advantage of BSG tag is that it's both higher performance and higher abstraction than these alternatives. By having things like no frame level synchronization, that out-of-band enable signal, we're able to clock much higher than a SPI bus. Without using multi-master pull-up resistors for I2C, we're able to just use regular standard digital logic to implement. It's a really easy way to integrate into your system. I touched on this a little bit, but one thing that happens in ASIC simulation is that it's very slow to simulate your annotated gate level simulations before you tape out your chip. And kind of the problem is that there's ways to abstract this configuration process, but this is really the most mission critical thing in your chip. So you want to have as high detail simulation as possible. But when you have a large number of configuration bits, especially if you're modifying them during runtime, this can have a huge simulation penalty to simulate with full accuracy. So by having this modest, say 4 or 5, 10x improvement over other protocols, you actually have a very large improvement in your overall configuration and overall GLS runtime. So future BSG tag, we want more people to use it. We've taped it out plenty. We'd love someone to do it in Sky 130. I hear there's very few pins on the MPWs, so that works well. More FPGA builds. We use Pink Z2s, Ultra 96s, a few others. Those are the ones we support. Love to see on a Lattice FPGA. Software and driver support. We have Python, C++ APIs. We'd love UVM, CocoaTB integration for native buses. And then we have those header files are generally handwritten for defining the registers, but we'd love to generate them using something like system-RDL. And yeah, so that's it. I can talk about BSG tag, open source ASICs. I do RISC-V multi-cores. So I'd love to connect with anyone at Latch-Up who'd like to talk to me.
Questions?
Super cool. Super cool. Thanks for the presentation. So I guess with this, you're able to actually send signals into the chip for bringup, but sometimes you actually care about what the configuration does and you want to read something out. Do you have some sort of extension to this so that you can actually read out values from that configuration bus, or do you just expect to expose more pins off your die or package to actually read out some signals?
Yeah, that's a great question. We typically have some mechanism for out-of-band responses. So generally some statically configured muxs that then we can have subsets of the chip read out those individual values. It's hard to do it in a scalable way to get all the signals out without doing like a scan chain.
Thanks. Yeah, like how complex would it be to bidirectional, like JTAG style, just shift something out,
You can do it. It requires a lot of tool chain integration usually to do it automatically, and it's a huge pain to do it manually. Yeah.
And you guys put this in all of your silicon now, right? So.
Oh yeah, many times.
Yeah.
We just brought up a chip with it actually like a month ago. So. Cool.
And how do you deal with the source synchronous thing? I always cheat and just shift the data on the neg edge and sample on the positive edge or whatever.
Yeah, that's effectively how it works. The basically the easiest way is you have an internal clock which is generating the tag, and you send the clock every other cycle, and then you send the data on the neg edge.
Cool. Yep. That's the way to do it.
Yeah.
Any other questions?
I'll pass a comment that for anybody who's not totally sold, we've used it and it works. We have multiple chips. It's great.
Awesome. Ringing endorsement. Oh, here we go.
To incorporate this in a chip, what % of the hardware would be required to implement this?
Oh, very, very small.
Okay.
I meant to run some synthesis before this talk, but you're talking on the order of dozens of gates. They're very, very small units.
Like dozens of gate per chip, or you had a slide earlier.
Yeah. So, for example, if you
per
have
IP, I mean,
you have obviously for each configuration bit you need to store the bit, so that will scale that way. But even in the synchronous case, you're storing 2 times the bits and then 3 other flops. So the overhead is fairly small.
Thank you.
Okay, I think that's all the questions.
Thank you.
Let's thank Dan again. Cheers, mate.